introduce the Professor Silon Perusato from the Federal University of the Pernambuco. Go ahead, Silon.
Okay, thank you. So let me start by thanking all the organizers for the kind invitations, in particular Roberto, for to be the chairman of this talks. It's been really nice to be here. In fact, because I'm a big fan of Lorenzo's work. So it's been really nice to be here. In fact, Lorenzo will be my postdoc supervisor in a few months, and I'm very excited about this. Okay, so let me say a few words about his career. Lorenzo Brandolese is professor, or I would say professeur at Université Lyon. Lorenzo finished, he received his PhD at École Normale Supérieure de Chacun under the supervision of Yves Meyer. His main research interests are asymptotic behavior of solutions to nonlinear PDEs arising in fluid mechanics. Mainly Navier-Stokes and Boussinesq, but also other parabolic and dispersive equations. These techniques are strongly based on harmonic analysis and are highly non-trivial, but at the same time, his methods are very elegant and very intuitive, I would say. So Lorenzo is going to talk about forcing rapid dissipation of Navier-Stokes flow. Go ahead with your talk.
Okay, thank you very much for proposing me to give a seminar at a talk at your seminar, and thank you so much for the nice presentation. So I'm honored. So I will present a joint work in collaboration with Takahiro Kabe from the University of Osaka. And just 1 second. Okay, I will start with an historical overview of the decay problem of the energy in order of solutions of the Navier-Stokes equations, just to put our result in a perspective. Only the second part I will state the main result and also give some elements of the proof. And I will finish, of course, with some conclusions. So let me consider the Navier-Stokes equations in their most classical formulation. So we assume that we have a viscous incompressible fluid which is filling the whole space. And the first equation, velocity u of x is the velocity of free particle at the point x at the time t, that is a vector field. The second unknown is the pressure, which is a scalar vector field. The second equation expresses the conservation of the mass, is the divergence-free condition. And we are going to be interested to the Cauchy problem, so we are given an initial data a of x. And this is how we write explicitly the quadratic nonlinearity. So a basic result about this system goes back to the 30s with if we start with an initial data, which is homogeneous understood with respect to the weak topology of L2. And then we have also an energy inequality for this inequality. The classical one is that this inequality holds for s equal to 0 and for all t larger or equal than s, and this is true in any spatial dimension. And at least in dimension 2, 3, and 4, there is a stronger version which is known to be true, also for almost all the solutions constructed by Leray goes to 0 in L2. And soon after, people started to compute explicit decay rates. For example, Schoenbeck introduced the Fourier splitting method, and putting additional assumption on the initial data, such as an additional LR assumption with R less than 2, she was able to compute the first decay rates, later improved by other people. And an important result appeared in '87 with Wigner, who succeeded in obtaining the optimal decay rates. So I will continue later on with the chronological presentation, but I will stop for a while to state in a formal way Wigner theorem, because it motivates the simple. So assume that the heat equation has some algebraic decay in L2. And by the way, this assumption can be reformulated in terms of function spaces. So the equivalent formulation is that A belongs to the intersection of L2 with a homogeneous Bevel space with negative regularity. Next, we consider any solution of Navier-Stokes satisfying the structure for the L2 at least when. So this means that large time behavior of Navier-Stokes and the heat equation is the same. In particular, this implies that from this decay assumption, we get the critical decay rate n plus 2 divided by 2. And in 2014, Scalak proved the so-called inverse Wigner theorem, the basics of this, then it must around the previous Bevel space. And we have this decay for the heat equation. And very recently, Professor Perusato and Paolo Zingano succeeded in giving a very elegant proof of this inverse theorem. And what can we say when sigma is larger than n plus 2 divided by 2? So it is no longer true that we have such behavior in the large time. And so this motivates the following definition. By definition, we say that a solution of Navier-Stokes is rapidly dissipative if the energy decays to zero, but faster than predicted by the previous theorem. And since Wigner's theorem tells us nothing, in this case, even the existence of such rapidly dissipative solutions is not so obvious. However, several examples are known, and the first example was given by Maida in the 90s, and is the vorticity of to check that in fact the non-linearity vanishes. And this means that starting from a divergence-free initial data, the solution of the Navier matrix, that is a scalar multiple of the identity matrix. Now, this condition is sharp, the assessment, but as you can guess, very difficult to check, simply because usually you don't know explicitly the solution of Navier-Stokes, so you are not able to compute explicitly this matrix, and you can't check this condition. However, what you can do in any dimension, in fact, is to start, for example, from an initial data that, in addition, possess some rotational symmetry, some discrete rotational symmetry. You take advantage of the fact that the Navier-Stokes equations is invariant under rotation, dissipative flow. And this is an example of a dissipative flow of Gallet and Jean Wayne, who adopted a quite different point of view because they worked with the vorticity formulation of dimensions solution. So this is interesting because the method can be used not only to prove the existence of a rapidly dissipative solution, but also to prove the existence of solutions however, point out the main part of the talk, and I will need some preliminaries first of all. So the first point is that from now on, I consider an additional external forcing that acts on the fluid. The external force will be I will take advantage of the fact that the Navier-Stokes system is invariant under scaling. So this is the usual scaling for Navier-Stokes. And this is the corresponding scaling for the and finite. Let us start with an initial data which is inside this Bezos space with negative regularity and divergence free, and with a forcing term in the space YR as before. We put smallest condition both for the initial data and for the force, and we get in this case the existence of global solutions of Navier-Stokes in the space XR, and also in the space X infinity, which is some kind of a first regularity information. And starting from this, one can prove also that in fact the solutions are strong, they are regular for strictly positive time. The solutions are unique in the ball of the space where you construct the solution, and you have also an information for the size of the solution. The first property that I will need is the boundedness from a YR to XR to get solutions that are velocity field in the space XR. And the second property is that I need the boundaries from some space to L2. And I can choose several spaces, L alpha, L beta space of space-time. But if you want to choose the simplest possible situation, for example, alpha equal to beta, then we get exactly this condition on alpha and beta. Okay, so let me state the result. Unfortunately, the statement is a bit technical, so I prefer to give some informal statement before. Okay, so roughly speaking, what I'm going to prove is the following: that if we start from an initial data, which is small in the same Bezos space as before, then we can prove the existence of a forcing term F. And this is a control force, so it is a force that it depends on the initial data, such that if we consider the Navier-Stokes equations with force the divergence of F, we get a unique global solution with additional information that this global solution is rapidly dissipative. But this first conclusion alone it's trivial. It becomes interesting only if you put additional requirement on the force that you are allowed to put. So what the interesting fact is that you can choose the force to be bounded both in space, to be bounded and more importantly, compactly supported both in space and time. More than this, you can achieve such a rapid dissipation effect by forcing the fluid just in arbitrarily short time interval. And in this case, the price to pay is that the spatial support of the force will spread out. Or if you prefer, you can just act with the force on a spatial region which is arbitrarily small. But in this case, the price to pay is that you have to act with the force for a longer but finite time interval. And the force can be constructed algorithmically. And the last point is that the profile of the force can be arbitrarily prescribed in the following sense. F can be obtained the following way. You fix a compactly supported bounded function chi, which is independent of the initial data, and then you just rescale and resize such a fixed function in an appropriate way. In an appropriate way. And this is how you construct the force. So F is just a rescaled and a resized version of chi. This means that basically you can achieve the dissipation effect by tuning a finite number of parameters. Okay, now to state the result in a proper way, I fix once for all an L infinity function of space-time, for example, which is supported in the cube. I need also the integral is not equal to 0, and I can normalize in such a way that the integral is equal to 1. And this is what we prove. Let R large the space dimension and finite. There exists eta 0, a small constant. there exists a constant symmetric matrix of size n, such that the entries of the matrix are bounded by 1, with the following properties. If we start with an initial data which is in the Bezos space and also in H-1, divergence free, and we choose the forcing term in this way, so we take our fixed function chi, we rescale it, and we resize it by multiplying by the H-1 norm squared of the initial data, and we use also the coefficient of the matrix. Then, provided that we have such size conditions on A, then we can get a global solution, which is in L2, and such that the difference between the solution of Navier-Stokes and the solution of the heat equation in the LQ norm for any Q is a little O of this negative power of time. And why this implies the rapid dissipation effect? Well, because as a corollary, immediate consequence is that we can put an additional assumption on A. We assume that A belongs to another base of space, B minus n plus 2 divided by 2 to C0. In this case, the solution of the theorem will be rapidly dissipative. And the reason is just we apply the theorem for Q equal 2. We get a little O of T to the minus n plus 2 divided by 2. And what is the role of this additional base of space assumption? Well, it is exactly the assumption that we need to guarantee that the linear part in the autonomous squared decays faster than the critical decay rate. Okay. And what is this new base of space? It is a subspace of the more usual base of space with SR infinity index, and the C0 condition simply tells you that the dyadic block goes to 0 in this sense. So it is an additional low frequency information. Okay, so now I would like to give some ideas of the proof, and the first tool will be an integral asymptotic formula, which is widely applicable. So it can be applied also besides Navier-Stokes. For this asymptotic formula, I need to have a kernel function, a function of x and t. The assumption is that it enjoys such rescaling properties. So particularly, we can deduce the kernel at time t if we have the kernel at the time 1. And we also assume that at the time 1, we have a function which is L1 and also in L infinity. In particular, it follows from these two conditions that f at the time t belongs to all LQ space with such decay rate. So this is the asymptotic profile that I'm going to apply. It is stated maybe in a new way, but essentially it is implicit in an earlier paper by Anna Carpio and by Fujikaki and Miyakawa. So it says the following. Assume that we have a function w in L1 space-time, and let us denote by lambda the space-time integral of w. We also assume that w is a big O of 1 over t when t goes to plus infinity in the L1 norm. And we use our kernel function f to introduce a new function phi by computing this convolution type integral. And the result states that in the large time, this function phi behaves exactly like the kernel, multiplied by the constant lambda, which is the integral of w. And this is true in LQ, at least when Q is close to 1, but if you put some additional assumption, then you can extend the range of validity of this asymptotic profile up to infinity. Okay? And so this is essentially implicit in Carpio paper. So I will not give details for the proof, but I will rather apply this result to Navier-Stokes. So first of all, let me denote with ET of X the heat kernel. And I'm going to apply the previous proposition with the kernel f, which is the kernel of this operator, e to the t delta p divergence. And what is p? P is the Leray projector. It is the orthogonal projector from L2 onto the subspace of divergence-free vector fields. Now, the divergence-free condition can be very easily expressed in terms of the Fourier transform. So the symbol of this operator is known explicitly, and then you can compute the inverse Fourier transform, and you get this explicit formula for the kernel f. So basically, this kernel is just obtained by computing spatial derivatives of the ith kernel combined with a time integration. And of course, this is very useful, and in particular from this, it becomes immediate to derive exactly the scaling property that we need to apply the proposition, and also the additional information of L1 and L infinity. In fact, this function f is smooth. So now let me write the Navier-Stokes equation in the integral form. This integral formulation of Navier-Stokes is the following. The difference between u and the solution of the heat equation by using the previous kernel can be written like a convolution with f, capital F of the forcing term, and then the analog of this term that is motivated by the nonlinear term. And I use this notation because we have a convolution indeed, but we have also a double summation because we have 3 components for the kernel, 2 components here for these terms. So we have a double summation on K and L, which is omitted here. And just to use the same notations as in the proposition, I call W this quantity. Now, let us assume, but this is an assumption. Let us assume that W does satisfy all the properties that we need to apply the proposition. Then in this case, we apply the proposition, and we derive this asymptotic profile for the solutions of Navier-Stokes, which is essentially the asymptotic profile already obtained by Fujikake and Miyakawa, with the only difference that inside the asymptotic profile, I incorporated the contribution of the forcing term. Now, to our purposes, we have to, okay, this means that the difference between the solution of Navier-Stokes and the heat equations in LQ behaves like a linear combination of the kernel multiplied by the integral of W. And this is true, of course, if the right-hand side here is not identically 0. And it turns out that it is possible to characterize exactly when this term is identically 0. This is identically 0 if and only if the space-time integral of W is a matrix which is a multiple of the identity matrix. So this is essentially the Miyakawa and Schoenberg orthogonality condition, with the only variant is that in this condition, we, again, once more, we incorporated the role of the force. So, summarizing, the goal is the following. Given an initial data, we have to construct a forcing term, and we have to construct a solution of Navier-Stokes associated to this forcing term, such that the force and the solution are related by the orthogonality relations that I mentioned before. So these are just the orthogonality relations before, but written explicitly. This is the first stage. The next step is to ensure that W does satisfy all the other assumptions of the proposition. Okay, so how can we construct such a force and such a solution? So the algorithm is the following. We start from an initial data that satisfies the Canone smallness assumption, and we fix once for all an L infinity function compactly supported in space-time. Just for simplicity, in fact, what I do really need is that I fix a function chi, which is in YR, and which also belongs to such a space. At a later step, I will also need that the integral is equal to 1. Then, so we start with a force which is identically 0 in the first step. We construct by Cannone theorem a global solution of Navier-Stokes in XR, which is also in L2 because we are working also with the H-1 assumption. And we have the size information for the XR norm. And then we proceed by induction. So by induction, we assume that at the step m-1, we do have a force and we do have a solution such that um-1 belong to the same space we're working with a good size estimates for the norms. In particular, we need that this L2 norm is bounded exactly by the H-1 norm of the initial data. And then using this, we construct the force at the step m. And so this is how we define the force at the step m. We just use the fixed function chi, and we multiply it by the matrix. And the coefficient of the matrix are used taking the space-time integral of the solution, the previous step, okay? With a modification when we are on the diagonal of the matrix. We have, by the inductive assumption, this information on the velocity field, so we can deduce that Fm is indeed well defined. We have also estimates for um-1 that imply estimates for the force Fm. Once we have this, we can once more apply Cannone existence theorem, but this time with the force. So we need a new size condition that both the initial data, but also the previous term that we get in the estimates are small. And if this is satisfied, we get the existence of the solution um. This solution um will satisfy the estimates that are granted by the Cannone's theorem, also for the L2 norm. We get these estimates, but just to close the inductive procedure, we need that this is bounded exactly by the H- norm of the initial data. And for this last inequality to be true, we need to put a last smallness assumption on the data. Okay. So basically, we have three smallness conditions that we need for this argument to work: the Bezos space condition and these two additional size conditions. But and if we have this, we can get a sequence of external forces and the sequence of solutions of Navier-Stokes. I would like to point out that in fact, only the first condition is really important. The second and the third one can also be dropped, provided that you replace chi by a different function, by choosing a different rescaling of the function. Such a rescaling preserve the L1 norm. Of course, if you do this, the price to pay is that perhaps you get a larger support of your function. Okay, there is a last step, which is the convergence step, because so far we just have a sequence of forces, a sequence of solutions. We can prove that, and here we skip a lot of details, we can prove that the sequence of solutions converges to a function u in all the function spaces that we need. In the same way, the sequence of forces will converge to a forcing term in the corresponding function spaces. And one proves that, in fact, this limit function u is a solution of the Navier-Stokes equations associated to a force, which is the divergence of this tensor F. And the quick outline is just the following. You do what you expect. You just compute the difference of your solutions at two consecutive steps of your algorithm. You perform some bilinear estimates in the Navier-Stokes equations to control in terms of the corresponding forces. You use the definition of the corresponding forces that relied on the solution at the previous step. And then you take advantage of your smallness condition that implies you that this term can be chosen to be less than 1. And so you get a convergent sequence. So this is the point where I need to choose that chi as a 1 integral. This is just to ensure that in the limit, the function f and the solution u are indeed related by the orthogonal conditions that we need. Okay. Now, we apply the proposition. And we get, owing to this orthogonality relation, that the nonlinear term in the asymptotic profile vanishes. And so the proposition in this case simplifies in the following way. We just get the LQ norm of the difference of Navier-Stokes and the heat equation that decays faster than the properties of the kernel mentioned before. There is some more work, which is quite long, but it is essentially straightforward, that has to be done, because for applying the proposition, I needed some additional estimate on W that I'm not proving here. But once you establish all the missing estimates, you get exactly this conclusion. Okay. So let me skip now to the conclusions. So the forcing term that we used is completely supported in time in particular. So this means that after some time t0, this force identically vanishes, and we already got a global solution. We know that such a global solution is rapidly dissipative. But since after the time t0 there is no more force that acts, U is in fact a solution of the free Navier-Stokes equations. And so there are two possible scenarios. The first scenario is that both terms that you have here and here, both they are individually rapidly dissipative. And this is in fact the scenario of the picture that I mentioned before when I put the symmetries, for example, on the flows. The symmetry that I mentioned before, in fact, implies that also the linear part of the equation is rapidly dissipative. But this is does not look at the generic situation. In the setting of this theorem, probably what happens is that both terms individually have a slow decay, but there is some nice interaction of these two terms, and so the individually has slow decay, but their difference has a fast decay. So this is probably what happens in the generic case in the setting of the theorem. And my last conclusion is the interpretation of this result in the Galilean theorem. So, for example, in 3 dimensions, what Thierry Gallet and Jean Wayne did is to consider an initial vorticity, which is in some space, which again is invariant with respect to the scaling of the vorticity equation. They put a smallness condition that guarantees, in a similar way as we did with Canonian theorem, this condition implies the existence of a global solution. They also needed to put some quite stringent localization assumption on the vorticity, so it belongs to a weighted L2 space. And they proved that there is a strong stable manifold invariant M of finite codimension in such a weighted L2 space, such that the solution is global and rapidly dissipative if and only if the initial vorticity belongs to this manifold M. So as I mentioned before, it is difficult to check whether or not omega 0 does belong to the manifold. So the interpretation of our result is the following. Whether or not omega 0 does belong to the manifold, our argument provides a procedure that in an arbitrarily short time force the solution to enter inside this manifold. Once the solution is in the manifold is invariant, and so it evolves into a rapidly dissipative solution. Okay. So this was the interpretation of the result, and I think that's all. I would like to thank you very much for listening to me. Thank you very much.
Thank you, Lorenzo, for this really, really nice talk. So now we are open for questions or comments. Are there any questions or comments? Please go ahead. Questions or comments? I have a question. I don't want to be too long here, but Lorenzo, exceptional flows which decay much faster do exist. For example, for any even dimension, you can construct a very particular solution which has an exponential decay in absence of external force, right? And my question
Yes, you're right. You're right. In 2 dimensions, it is the same. Okay, I don't know. Sorry, maybe I'm interrupting you. So please.
Yeah, no, but my question is the following. Can we obtain an exponential result for generic flows in the presence of external force, adapting your argument, or it's not possible?
So it is true that there are a few examples of solutions of Navier-Stokes with exponential decay. So in this picture, we have the example in 2 dimensions, and as you mentioned, it is true in even dimension because you don't have a topological obstruction that occurs in odd dimension. But in fact, I would expect that with an improvement of this algorithm, I could get solutions with algebraic decay at arbitrarily fast decay rate, but I'm not sure that I can get the exponential decay with the force intern.
Oh, okay.
At least it depends on how much you ask on the force, because if you allow the force to be anything, okay, you can of course you can trivial way you can force the solution to be identically 0 after some time, but if you put constraints on the force, it becomes tough.
Yeah, okay. And I have just one last question. Where exactly do you use the smallness condition on the initial data? I mean, it's possible to obtain the same rapid dissipation, at least for the 2-dimensional case, without us assuming such condition.
You are right. Yes. In the 2-dimensional case, this is indeed possible. I was not able to remove the smallness condition in high dimensions.
Okay.
Basically because I thought about this, but I had a difficulty working, for example, in the setting of weak solution. I met the difficulties at some point. For example, if one uses Leray solutions, we have the existence of Leray solution is proved by compactness arguments, but the topology in which the approximate solutions converges to the weak solutions is not strong enough to get the orthogonality conditions.
Yeah. Okay, thank you, Lorenzo, for clarifying answers. So, are there any more questions? Roberto, please go ahead.
I have just a curiosity because it's not my main area, but when you are in a manifold, 3D manifold, do you have, for example, put some assumption of the geometry of the manifolds, or not necessary? Any information geometry? Because, for example, for this specific equation, when you have to see the decay, in some sense, you need to take care with the geometry of the manifold.
Well, in fact, we don't know a lot about this manifold. What is known, basically, there is a proof of the existence of such a manifold. What is possible to do is also to compute the codimension of the manifold in the function space. And so this it gives some hints on how many solutions there are which having such a fast dissipation effect. And besides this, not so much is known about this manifold. Okay, it is known about the geometric properties. It is known that this manifold has some, it is flat along some directions. And this is essentially due because this manifold must contain some vector spaces that are essentially the vector spaces that are constructed putting the symmetries. Okay?
Right.
And this is essentially all what we know, all what we know about this manifolds.
Okay. Thank you. Just a curiosity. Thank you, Professor Lorenzo.
Thank you.
Okay, any more questions or comments? So let's thank again Lorenzo.
Thank you very much.
My pleasure for your beautiful talk. Okay, so now I give the floor to Roberto, I would say, or.
Okay, thank you, Juan, and I will turn off the record here. I will stop. Okay.